All right, and welcome to the recitation lecture for Chapter 19 on thermodynamics. This is going to be a relatively straightforward one. I think we've got 5 questions for today. And let's go ahead and kick it off with, and of course, like previous ones, I'm not really going through conceptual style questions as much as calculation-based questions, just to get people comfortable with some of the operations that would be styles of operations we'd be expecting on an exam coming up here. So let's see, question number 1. Above what temperature does the following reaction become non-spontaneous? And so for the reaction, we here have solid iron oxide plus carbon monoxide gas reacts, forming carbon dioxide gas and solid iron. So we're just abstracting the oxygen from the iron oxide to form CO2. And we have given values of enthalpy of a negative 11.0 kilojoules and change of entropy for the reaction of negative 17.4 joules per Kelvin. So for this, what defines spontaneity? And to determine whether something is spontaneous or non-spontaneous, we can lean on either K or delta G. In this case, right out the gate, we have thermodynamic terms for enthalpy and entropy, and that indicates that we're probably interested in delta G, and that takes us all the way back conceptually to what temperature. So if we are thinking delta G equals delta H minus T delta S, this is probably what we're working with. And we're wondering, what's our temperature of non-spontaneity? Well, at what temperature is something non-spontaneous? It's incrementally different from where it's at equilibrium. And what's equilibrium? When delta G equals 0. So I'm just going to set this entire term equal to 0. Where delta G equals 0, it's at equilibrium. If we're incrementally different from that, we're going to be non-spontaneous. So now we can just use this relationship to solve for T, and that's going to give us the temperature at which we are able to become non-spontaneous. And I'm just going to add the term T delta S to both sides. Giving us this relationship, and then I'm going to solve for temperature. And now what we have, a working relationship, I can substitute and solve. So for delta H, we have negative 11.0 kilojoules, but I'm going to put these in joules because I want our terms to cancel. So I'm going to call this 11,000 joules, and delta S is negative 17.4 joules per Kelvin. Joules is going to cancel, so we have 1 over K, which is just K as our unit, and so temperature solves to 632 Kelvin in this case. And if it was asking for Celsius, you just subtract 273.15 from that. So nice way to warm up, get started here. Oh, let's see here. There we go. Scrolling. Whoa. Let's see if I can scroll a little bit more analog, a little less digital. Okay, so problem 2. Determine the equilibrium constant for the following reaction at 298 Kelvin. We have SO3 gas plus H2O gas reacts forming sulfuric acid liquid. And we get a delta G naught of negative 90.5 kilojoules for this particular reaction. And this, what we want to know is, what's the equilibrium constant? We have the handy-dandy relationship which relates our equilibrium constant K to delta G, and that relationship is delta G equals negative RT ln K. So remember, R is 8.31 joules per mole Kelvin. Temperature has to be in Kelvin as well. And we are trying to solve for K. So what I'm going to do right away with this is just isolate the natural log of K. And then once we've solved for the term, we'll eliminate the natural log. So let's just go ahead and plug and chug here. We've got a delta G of negative 90.5, and this is also in kilojoules, so I'm going to move it into joules because R is joules per mole Kelvin, and we want our terms to cancel. So we'll say this is negative 90,500 joules. R is 8.31 joules per mole Kelvin, and T in this particular case is 298 Kelvin. So Kelvin's going to cancel, joules is going to cancel. We'll have 1 over moles, which is moles. This is assumed per mole compound, so it will become unitless when we move to K. And let's see what natural log of K is. This is going to solve to be negative 36.54. Excuse me, it's not negative 36.54. It is a negative over a negative. I almost missed that. Very brief negative. So now what we need to do is raise both sides to e to eliminate our natural log. So K is going to be about 7.4 times 10 to the 15. A very, very nicely positive equilibrium constant. Which makes sense because it has to be positive because delta G is negative, and both of these expressions indicate a spontaneous reaction. All right. Third one. Ooh, these are always fun. Let's see what we can do here. So, using Hess's law to calculate delta G naught for reaction, using the following information. The reaction we're interested in is this first one here. So, what we need to do is balance the following three reactions so that they are arranged in such a fashion that they equate to the above reaction. So let's see how we can do that. Well, on the reactant side of our first reaction, let me just erase this. We have NO, we have oxygen, not O2, just oxygen, monoxygen, and we have on the reactant side NO2. So where's our NO? Let's find it. Well, here we go. We've got our NO on this side, and we've got NO2 on the opposite side. So we've accounted for two of the three things that we have to deal with. And so the rest is going to be in the details here. And then what we notice right away is we've got an O3. Oh, excuse me, let's go back to the beginning. We've got an oxygen. So where's that? It's in our second equation. And we see that O2 gas goes to, in this half reaction, to two equivalents of oxygen. So what we're going to have to do is we're going to have to put that on the opposite side. So let's see if we can balance this out here. I'm going to do a rewrite. So we have these two components that I talked about already, our NO and our NO2. And what I'm going to do is I'm going to rewrite this second equation backwards. And so instead of O2 goes to two oxygens, I'm going to say that we have two oxygens going to O2. Now right out the gate here, you're going to say, yeah, but Dr. McGill, there's a 1 there. There's not a 2. Well, we'll be able to deal with that in a second. What else do we have to deal with? Well, we have to deal with the presence of O3, in the mix here, because we need to get rid of that. Well, our first equation, we have O3, 2 O3s go to 3 O2s. So to get rid of that O3, we need to put it on the opposite side. So let's see here. 3 O2s goes to 2 O3s. And you say, man, but we have too many of these. Well, if we end up with a single oxygen, what if we're going to make everything worth 2 times here. So let's just multiply this whole first equation by 2. So I'm going to put a 2 here. 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 And we can do that as long as we take our delta G term and multiply it by 2, right? So that's all fine. So let's see what this gives us. Well, now we have 2 O3. Maybe let's see if I'm going to draw here. I'm going to grab a red pen. 2 O3s cancel each other. Nice. And then we have 1, 2, 3 O2s, and we have 1, 2, 3 O2s. Those cancel. And what we're left with is 2NO, 2O, 2NO2. So if I was to rewrite this, this is what we'd have. And this is now our desired equation up top, just times 2. So if we sum everything as drawn in terms of our delta G half reactions and then divide by 2, we'll end up where we want to be. So let's go ahead and do that. Close this help down. Okay, so for our first half reaction, what we did is we drew it exactly in the order that it was originally drawn, from left to right. However, we multiplied everything by 2. So delta G for this half reaction, wow, that's all just disappearing. Let me see if I can fix that. Oh, so I'm going to go back to standard drawing tools. So delta G for this first reaction is just going to be negative 199.5 kilojoules times 2, which is negative 399 kilojoules. The second half reaction, 2 oxygens goes to O2, is what we see here in our second half reaction, except that it's drawn in the opposite direction from what was described. So as described, it was positive 463.4 kilojoules, but because we drew it backwards, to balance this, it's going to be negative that, negative 463.4 kilojoules. And then our 3 O2s goes to 2 O3s is the same situation where it's also been reversed. So instead of positive 489.6, it's negative 489.6. And then we can add this all up, and this would give us negative, that's ugly, let me rewrite that. Negative 1,352 kilojoules. Now, we're not done yet, because all of our coefficients are in its most reduced form for this first equation. They're all 1. So I'm going to divide everything by 2, which means that we will end up with a negative 676 kilojoules as our term for the delta G naught reaction of our overall balanced equation. Whew. There was a couple operations there, but that's not too bad. Those are always fun. Let's see, problem number 4. Calculate delta G of reaction at 298 Kelvin under the conditions shown below for the following reaction. 2 equivalents of mercury gas plus O2 gas react to form 2 equivalents of mercury oxide. We have a delta G naught of negative 180.8 kilojoules. And we have the pressure of the gaseous components given. And what we're really interested in here, and this is the important point of this, what's our delta G of reaction under these non-ideal conditions? Because ideal conditions dictate we have an atmosphere for our gases. This is non-ideal. So we're losing that naught, and we're actually interested in how delta G naught is adjusted for non-ideal conditions. And we only have one equation that we need to concern ourselves with for that kind of situation, and that's delta G for reaction equals delta G naught of the reaction plus RT ln Q. Remember, Q is just like K, except under non-equilibrium conditions. So let's sort this out. We've got delta G for the reaction. It's given. We know what R is, because R is always 8.31 joules per mole Kelvin. Temperature in this particular case is standard, 298 Kelvin. So all we need to do is find Q, and Q is like K. So Q, like K, is going to be products over reactants. Now, our product's a solid, so it doesn't factor into this equilibrium system. So 1 for our placeholder. Well, we can, remember, do this for concentrations. We can also do it for pressures. So let's take a look at the pressure of mercury in this case, 0.025 atmospheres, and we have a coefficient to deal with. We've got to square that term. We also have oxygen, 0.037 atmospheres. Notice no coefficient. Well, there is. It's just 1, so we don't have to square it or do anything else because it's just 1. And Q, in this particular case, is going to be, let's see, a little math, negative, let's see, what am I messing with here? I'm going to have to break out the calculator. Sorry, guys. Give me a second. Some of you are probably doing this on a calculator right now faster than I am, because I continue to mash buttons incorrectly. Okay, I got 43,243 for Q. And we might as well just do natural log of Q to save ourselves some time. That's going to be 10.67. Okay, so let's set this whole thing up now, because we've got everything we need. Delta G for this reaction is going to be the delta G under standard conditions for the reaction, which is negative 180.8 kilojoules, plus negative 8.31 joules per mole Kelvin, (298 Kelvin), and 10.67. And what we're going to end up with here, there's no negative here, sorry guys, is negative 154.4 kilojoules, because once we adjust for joules going to kilojoules on this term. Just a little correction. You can see in this particular case, delta G actually increased, became less negative. Therefore, if you were to be asked, does the set of conditions make the reaction more or less spontaneous than standard conditions, you could say these would be less spontaneous than standard conditions. And finally, problem 5. Calculate the change in entropy under standard conditions for the reaction for the following reaction. And we are given standard entropies for each of the species. So this should be really straightforward. We have C2H2 plus H2 goes to C2H4, all in gas phase. We're given standard entropies for each of these compounds. So delta, remember, is just final minus initial. Wow, we're finishing off with a super easy one. Remember, it's always just final minus initial. So delta is final minus initial, which means products minus reactants, and we just need to sum everything. And everything's 1 to 1 to 1, super straightforward. So we could just say that our delta S for the reaction is going to be the sum of all of our products, which is just going to be 1 times 219.3 joules per mole Kelvin, minus the number of moles of C2H2, which is 1 times 200.9, plus the sum of all of the moles times H2, which is 1 times 130.7, and this is going to give us a negative 112.3 joules per mole Kelvin. So we have a negative delta for our entropy term, which makes sense because we're going from more molecules to fewer molecules, so we're seeing a decrease in entropy here. So that actually passed the rationale test. And that's the 5 problems for today's mini recitation. I encourage you guys to take these examples, go back to the homework, look at analogous styles of questions and variations on these themes, and get a little bit more practice in. Make sure you also get in some of those discrete conceptual questions, because there will be a handful of those on the exam as well, which I'm not reviewing because there's plenty of direct practice of those in the homework. And I hope this helps. And we have one more chapter coming up, electrochemistry, and that's going to be it for the semester. So almost there. Everyone stay on it. Just a few more weeks. We've got Thanksgiving coming up, and we're on the very tail end of Chem 106. All right, talk to you all later. Bye-bye.